Hi everyone, my name is Madeline MaGee. I work at the Wisconsin Department of Natural Resources, and I am the chair of the Great Lakes Working Group of the Wisconsin Initiative on Climate Change Impacts. And today I'm going to be giving an overview of climate change impacts in the Great Lakes. So to start off, let's just address the most basic question. Why is climate change important? Well, climate impacts all components of the Great Lakes ecosystem, and climate change is going to have vast consequences throughout the ecosystem, and it's going to impact how we manage our ecosystem and how we manage the Great Lakes overall. So understanding the impact will help us become better stewards of the lakes. Before we dig into the details, I want to start with a kind of an overarching framework of how climate impacts our ecosystem. And the answer is that it can be a little complicated. And we want to understand this complication because understanding the mechanisms of change will really enable us to develop quality adaptation solutions. So, most directly, when we're trying to think about habitats and the species that we manage in the Great Lakes, climate can impact those species, directly. Air temperature changes can alter where species may be adapted to live. Precipitation can do things like affect available habitat, for example, coastal wetlands. And these changes are, maybe not easy to adapt to and easy to address, but they're certainly easy to make the connection between climate change and habitat and species and try to plan for these changes. But where things get a little complicated is when we start to consider indirect changes. So climate change can directly impact water quality changes, such as the loading of nutrients into the lakes or the occurrence of harmful algal blooms. It can also directly impact physical lake changes, like water level changes and water temperatures. And these two changes can first interact with each other. So lake physics can indirectly impact water quality changes, but then they in turn can also impact habitat and species. And when we consider this as a whole, it then becomes not quite clear what the climate change may be. We have these direct impacts to habitat and species, but we also have indirect climate impacts as they act to change water quality or lake physics, which then impact habitat and species. And these indirect impacts from climate change can make things a little more complicated to plan for and adapt to. In this talk, I'm going to cover how climate changes and then go into how lake physics, water quality, and biota can all be impacted by climate changes so that we have a base to start from to develop holistic management strategies for adapting to climate change. So first, let's get started on how climate is changing. It's hard for us to figure out what the impacts are going to be if we don't first know what the actual climate changes are, right? I'm going to start with air temperature changes. Many of you are likely familiar with the fact that global air temperatures have been increasing over the last 100 or 150 years or so. And air temperatures throughout the Great Lakes have also been increasing. According to a report done by the Environmental Law and Policy Center, the Great Lakes region is actually one of the most quickly changing regions in terms of air temperature increases worldwide. And over the whole region, that average air temperature has increased by about 2.3 degrees Fahrenheit since 1951. And there are many different studies looking at changes in air temperature over different time periods, over different regions in and around the Great Lakes. And they do all come up with a slightly different value for what the average air temperature increases have been. But the consistent message from all of these studies is that air temperatures are increasing and they are increasing at a significant rate. And what is also very important and interesting to consider is that those changes, while we look at the whole, we can see, one average change, there are spatial variations in those changes. So if we look at this map here, we can see that the southern region of the Great Lakes has been increasing slightly less than kind of this northern northwestern region, with northeastern Minnesota having the highest air temperature increases that we see, at least on the US side of the border. So air temperatures have been increasing and they will continue to increase further. All models show that we are likely to continue seeing drastic increases in air temperature throughout the basin. Consistently across the models, we show a slightly larger increase in more northward areas compared to temperatures in southerly areas of the Great Lakes Basin. And all models additionally show air temperature increases for all 4 seasons. So just like our past data, we're getting consistent messaging for what to expect in the future. Warmer air temperatures in all 4 seasons, with more northerly areas of the Great Lakes Basin being more affected than the southern areas of the basin. Next, moving on to precipitation, over the last 50 to 60 years or so, we've seen an increase in total precipitation in the Great Lakes region, as well as an increase in heavy precipitation events. So total precipitation has increased across the basin by about 14%, and heavy precipitation events have increased by about 35% over that same time period. Unlike air temperature models, models anticipating future precipitation changes are not in agreement. All models do consistently show robust increases in winter and spring precipitation. The figures on this slide show expected precipitation increases in winter on the left and spring on the summer to Wisconsin by the mid-century. So these are increases from the 1980 baseline to about 2055. And you can see that similar to our projected air temperature increases, we see a greater rate of change as we move northward. And these are pretty consistent in the models. However, ensemble models show variable results in long-term changes in summer and fall. So we can't really say with much certainty whether we will have increases or decreases in those months, or whether things will stay kind of along the average precipitation that we've seen over the last century. Our best estimate right now is that for summer and fall, we will continue to have more extreme events, longer and more intense drought conditions, but also more extreme storm events and more rain during wet periods. Now, moving on to wind speed, we have even more uncertainty. Globally, we've seen a phenomenon called atmospheric stilling, which is generally leading to lower wind speeds in our region. However, climate change can cause a smaller temperature difference between air and lake water, which actually leads to higher wind speeds across the lake surface. We do also expect that more extreme storm events associated with increased precipitation events can lead to higher wind speeds during these events, even though the average may not be drastically different. So the long and the short of wind speed is, it kind of depends, and we may need to plan for both lower average wind speeds, but greater increases in extreme wind events. Next, I want to move on to how are the lakes changing? How are these climate changes directly impacting changes to our lakes? I'm going to start with physical variables of the lake. So let's start with ice cover. Should not be surprising that with warmer air temperatures, we've seen decreasing ice cover on the Great Lakes. And we expect that we'll continue to see decreasing ice cover moving into the next century. And ice cover is very important because it plays a role in protecting the shoreline and nearshore habitats in all 5 of the Great Lakes, especially during January and February when winter storms are often the strongest. So decreases in ice cover can impact habitat and species that live in the Great Lakes. This is an example of an indirect climate impact, where climate is impacting ice cover, which is then in turn impacting our habitat and species. Moving on, let's talk about warming water temperatures. Between 1976 and 2013, we've seen an increase in surface water temperatures in all of the Great Lakes. Lake Superior is actually one of the fastest warming lakes in the entire world and is increasing in temperature faster than air temperatures are increasing. And while we haven't looked at most of the Great Lakes, a recent study came out earlier in 2021, showing that Lake Michigan's bottom water temperatures are also increasing at a significant rate. These warming temperatures can have impacts on biota within the lakes. Even small changes in thermal characteristics of the lakes can have large ecosystem consequences. And this is especially true in nearshore areas where a majority of the biota spend important portions of their lives. Water levels are a topic that we've seen in the news recently. Water levels are determined by inflow into a lake from the upstream lake, outflow from the lake into the downstream lake, and something called net basin supply. Net basin supply is the combination of water leaving the lake through evaporation and water entering the lake through precipitation and runoff. For most of the Great Lakes, inflow and outflow are managed and fairly consistent from year to year. However, net basin supply is determined by natural processes that humans can't manage. The first term, evaporation, is generally expected to increase with climate change because of warmer air temperatures and warmer water temperatures. So during times of drought or low precipitation, we expect that evaporation will dominate net basin supply, leading to lower water levels. But during times of increased precipitation and runoff will be increased compared to evaporation, leading to increases in lake levels. Because of this tug-of-war and variability between evaporation and precipitation and runoff, we ultimately expect that moving into the future, we will have higher highs, lower lows, and more variability in water levels compared to the past. Next, let's start talking about water quality. Increased precipitation and corresponding increased runoff leads to higher nutrient loads into lakes. These increased nutrient loads can exacerbate existing water quality issues and create new issues where they previously didn't exist. You can see an example of this here from the MaGee River entering Lake Superior. Multiple 500 to 1,000 year storms over the last decade have caused huge nutrient and sediment plumes to enter the lake. This is a particular concern in the nearshore areas of the lake where decreased water quality can impact available habitat for species as well as alter aquatic food webs. These increased nutrient loads into the lake, combined with warmer water temperatures, may lead to increased algal blooms in some areas of the Great Lakes. In some areas, this is primarily due to increased nutrient load and warmer temperatures, creating more ideal conditions for harmful algal blooms. In some lakes, for example, Lake Superior, we believe the existence of algal blooms recently is actually primarily caused by warmer water temperatures alone. So what do these climate changes, water quality changes, and lake physical changes mean for habitat? Erosion and sand transport is a normal process in the Great Lakes. So let's go through a quick diagram here. We have a shoreline shown here on the left, and we have wave action kind of impacting the shoreline. Eventually we have erosion, which takes away some of the soil. And then as that erosion increases, we can get sloughing of the bluff off into the water. And then things like groundwater input, rain, and wind can then cause a new shoreline to form that's farther back from the original shoreline. And this is kind of an existing process that happens all throughout the Great Lakes. However, climate change increases erosion of the shoreline during both high and low water levels. So as already discussed, we have seen and expect to continue to see more extreme storm events. These stronger storms result in stronger waves battering the shoreline, which can increase shoreline erosion. Additionally, the most extreme storm events generally occur during the winter periods. When there's ice cover on the lakes, ice can act to protect the shoreline from storm damage and can decrease the likelihood of erosion. However, increased storms, combined with less ice cover during the winter, ultimately leads to more erosion as stronger waves bombard an unprotected shoreline during the winter months. And we see this in all kinds of systems in the Great Lakes, both natural on Lake Superior on the left and more developed shorelines on Lake Michigan on the right. And this erosion can cause the loss of both shoreline and nearshore habitat as material can fall into the lakes and smother spawning and nursery habitats. Fluctuating water levels can also alter shoreline habitat. Although we prefer things to stay in a kind of homeostasis condition, water level fluctuations and corresponding changes in shoreline habitat are part of a healthy Great Lakes ecosystem. However, sustained changes in water levels or very fast changes in water levels can cause permanent shoreline habitat changes. For example, let's look at this location along Lake Michigan in 2001. Please note the willow tree highlighted for reference. So this is the normal condition of the beach. There's been some gradual, shifting of where the water levels are over the long term, but generally the shoreline vegetation did not change drastically through this time, and the only changes are just how much of the beach was inundated with water. Now, if you look at the year 2013, where we had low water levels, we start to notice that we now have terrestrial plants established on the shoreline because of these sustained low water levels. Terrestrial species have started migrating towards the water. Normally, there would be enough variation that periods of slightly higher water levels would prevent establishment of terrestrial species along these locations. Now, if we start to look at the year 2016, we see that water levels have started to rise and the water is approaching these terrestrial species that were established during the low water period. We see increased vegetation compared to the normal condition in 2001, but some sandy beach habitat has returned because of these higher water levels. And if we fast forward to 2019, where we had close to record high water levels, we can see that most of the shoreline is now either inundated or completely eroded away. And I want to stress here that some shoreline change is normal and to be expected, and we should plan for it. But the issue from climate change is sustained periods of high or low water levels and then quickly rising or falling water levels that can cause permanent changes to the shoreline and impact the ability of vegetation to naturally kind of migrate towards the water or landward as water levels change. As I'm sure you all know, coastal wetlands are very important habitats in the Great Lakes. They provide fish spawning and nursery areas, habitat for birds and mammals. They help protect the shoreline during large storm events and help remove nutrients and contaminants before they enter the lakes. But coastal wetlands are one of the most vulnerable habitats to climate change. As discussed on the previous slide, they're particularly sensitive to water level fluctuations, especially sustained water levels, which can cause permanent community changes or very quick water level changes because plants within the wetlands may not have time to retreat or advance to follow changing water levels. They're also sensitive to increased storm events, which can physically destroy wetland habitats, especially during winter months if ice cover is not protecting them. Changes in air temperature and precipitation directly influence physical and chemical variables associated with fish habitat as well. As I described earlier in this presentation, these can include changes to water temperature, water clarity, and nutrients. Warm, cool, and cold water fish are expected to have increased thermal habitat within the lakes as a whole, but likely in different areas than they occupy currently. So cold water fish habitat, for example, may extend towards northern and deeper portions of the lake, while warm water species may move into new nearshore habitats. Warming tributaries may mean less spawning habitat for migratory fish, and nearshore spawning habitats are at risk from erosion and from storm damage. Wind from storm events can physically displace and damage eggs and cause rapid temperature drops from upwelling, which can cause mortality in some spawning areas. Finally, increased nutrient loads can decrease water quality and potentially lead to increased hypoxic conditions, as may be the case in the future for places like Green Bay. So what do these habitat changes mean for species themselves? First, we expect that climate change will lead to changes in species distribution for both aquatic and terrestrial species. Most of you may be familiar with this idea of thinking about what vegetation will be able to survive in warmer temperatures. Maybe a longer growing season will lead to more heat-tolerant species migrating northward, or cold-tolerant species not surviving because seeds can't germinate in warmer temperatures. But this same thinking applies to aquatic and terrestrial animals as well. Some bird or reptile species may migrate northward if they cannot stand warmer temperatures, and new, warm-tolerant species will likely take their place. The same also happens within the lakes. Cold and cool water fish species may migrate to more northward areas of Lake Michigan, for example, or may be extirpated entirely in some areas and replaced by warm water species. One of the greatest potential threats to species in the Great Lakes is facilitation of species redistribution and introduction of non-local species to the region. If we think about non-local species coming to a new system, there are kind of three filters to determine whether they will negatively impact native biota. The first filter is whether or not these non-local species can even reach the new ecosystem. And we expect with increased travel, increased shipping, and just increased use of water as a recreation source, that there will likely be increased pathways and more opportunity for non-local species to reach the Great Lakes. If you look at the second filter of establishment, climate change is likely to create ideal conditions for non-local species, allowing them a greater chance of developing a self-sustaining population. And then finally, if we look at the last filter of adverse impacts, we know that many of our species are going to be stressed because of climate change alone. So the introduction and impact of non-local species is likely to be higher and likely to magnify the impacts of climate change if they're allowed to reach our system. So warmer conditions may lead to increases in invasion success and increase the impact of non-local species that are already present in our ecosystem. For example, climate change has the potential to both produce more favorable conditions for sea lamprey and to reduce the effectiveness of control efforts in the Great Lakes. Ultimately, this will lead to a greater impact from sea lamprey than if climate change was not an overarching factor in the Great Lakes. Climate change can impact all trophic levels within the lake and the shoreline. In the Great Lakes, we expect increases in primary productivity and changes in plankton community composition. In Lake Superior, for example, rapid increases in primary productivity have been attributed to increasing surface water temperatures and a longer growing season. Changes in water quality, especially harmful algal blooms, can also impact the aquatic food web. And invasive species may present the largest threat to food web restructuring, as we've seen in the past with Dreisseniid mussels. So while we don't have a great prediction of how aquatic food webs will change, we have identified many mechanisms related to climate that would cause restructuring of food webs, and this is something that we need to consider as we're moving forward with our climate adaptation plan. In terms of climate change impact to fish, it's a bit of a mixed bag. Some climate changes have advantages for some species, while others will be disadvantaged by those same changes. A few slides ago, I described impacts to fish habitat, which will result directly in winners and losers for different species. But climate can impact other components of fish as well. For example, warmer water temperatures will likely increase fish growth. However, to sustain that growth under warmer conditions, fish will need increased prey availability and increased habitat. So a species may be a winner or a loser depending on whether the prey and that habitat is available or not. If it's not available, warmer temperatures will likely result in that species being a bit of a loser because they won't be able to find enough food to maintain their metabolic conditions. Increasing water temperatures can also impact spawning. Spring and summer spawning species are likely to benefit from warmer temperatures because research shows they have a higher recruitment with increased water temperatures. However, warm winters may reduce egg quality and hatching success for fall and winter spawning species. Warming can also cause a mismatch between spawning timing and food availability. In general, our winter species will be those that are more tolerant of pollution, likely more warm water species, assuming there's enough available prey, those that spawn in the spring and summer, and probably those that are invasive species. Losers will be fish that are less tolerant to pollutant conditions, cold water species, fall and winter spawners, wetland-dependent species, and some specific species like cisco, brook trout, and lake trout. In addition to direct and indirect changes to habitat and species that I've already described, it's important to note that climate change is a threat multiplier. It exacerbates existing issues and threats, making already existing stressors more likely to cause negative impact to the Great Lakes. Threats such as poor water quality, invasive species, and habitat destruction are all amplified with climate change. So for an example, let's consider the impact of non-local species on our native species. So we know that generally, increased invasive species will lead to negative impacts for native fish species. This can be because they prey on native species, or maybe they just outcompete them for limited resources. So if we lay climate change impacts over top of the impact of invasive species, we know that climate negatively impacts fish species for some of the reasons that we've discussed in this presentation already. But climate change can also make habitat more suitable for invasive species. So we see that we get an extra little bonus for invasive species and then an extra minus for the native species. But climate change can also enhance just the negative impact of invasive species themselves. So we see at the end of the day, while invasive species have a negative impact on native species in general, when we overlay climate onto that, we're multiplying the impact of invasive species to our native fish species. So, to summarize and conclude, I want to go back to this slide. How does climate impact our ecosystem? When we are considering the impacts of climate change to our particular areas, we need to consider the direct impacts of climate changes on habitat and species. Things like rain shifts from direct air temperature changes, or suitability of species under new temperature and precipitation regimes. But we also need to consider climate's indirect impacts to the ecosystem. To fully develop a climate resilient system and develop comprehensive adaptation strategies, we need to consider all of the impacts from start to finish. If we miss some of the indirect changes or don't consider them in our adaptation planning, we may not be setting ourselves up for success. Finally, all the information I presented here today are general changes and things that we need to think about and consider for each of our projects. However, I do want to point out that all climate impacts, as well as their solutions, are place-based. We don't expect the climate impacts here to be the same as those here, or to be the same as those here. If we want to develop comprehensive adaptation solutions, we need to make sure we are considering place-based impacts and place-based solutions. I'd like to wrap up by leaving you with some resources as you move into climate change and adaptation planning. First, the Wisconsin Initiative on Climate Change Impacts has put together lots of resources on a variety of topics. While it is specific to Wisconsin, much of the information applies to other areas of the Great Lakes. NIACS is a great resource for adaptation planning, and their adaptation workbook and adaptation menus are phenomenal. The Environmental Law and Policy Center came out with a report in 2019 detailing impacts of climate change on the Great Lakes. This is a great place to start when you're trying to figure out what may be impacts in your area. GLISA is also a great resource for climate change impacts. And finally, the U.S. Climate Resilience Toolkit has some great resources on impacts and links to other adaptation approaches and options. Thank you for your time, and I wish all of you luck on developing adaptation strategies for your project site.